problems with general relativity? So, first of all, let me just say the following. There are no experimental problems with general relativity that we can see right now. Okay? In particular, every experiment that we have done in real life has perfectly shown you, has perfectly matched the predictions of general relativity. It's really quite amazing and brilliant. Okay? However, there's again a sort of conceptual problem which might be important for some things, which I will now discuss. The problem with general relativity is the general relativity doesn't actually work that well with quantum mechanics. Okay. Now, let me explain what this means. Again, quantum mechanics is a huge and very important subject that I will not be able to explain properly in these short videos. But quantum mechanics sort of implies something about how forces work. Okay? So let me explain what that means. So, what is a force? So, for example, a force which we all know about is the electromagnetic force. Okay? So let's imagine you have two charges, two electromagnetic charges, and they feel a force between each other. Okay? Now, when we're first learning about these forces, we think that a force is just something that happens between two objects. But it turns out that if you think about it very hard, and you think about it remembering that quantum mechanics is important, a force is actually many little particles flying back and forth. Okay? In other words, if you look very closely, and by closely I really mean something very technical, but if you look very carefully at two objects that are charged, then you'll see many little particles that fly back and forth and carry that force. Okay? So for example, for the electromagnetic force, those particles are called photons, and they are really the same things that create light. They are the reason why you can see me right now. It's because your computer screen is doing something with the electromagnetic field, which is creating photons which go and hit your eye. Okay? But the idea is that all forces come with an associated particle. Okay? So for the electromagnetic force, which is sort of the most familiar force, they're photons. There are other forces in the universe. There are things like the nuclear forces and the strong nuclear force and the weak nuclear force. Those have associated particles. I'm not going to tell you about them, but you can look them up. But the main point is that everything that feels the force creates these particles, and these particles then just sort of fly back and forth between the objects. Now let's think about gravity. Okay? So gravity, as we discussed earlier, is really the curvature of space and time. And in particular, what that means is that everything feels gravity. Okay? And you sort of know this already, right? You know that no matter what you can do, you can never stop feeling the force of gravity, right? You can't escape from gravity. If you have to climb some hill, you know you have to climb it. There's nothing you can do to make the gravity any less on you. Okay? Let's think about what that means for the particles that would carry the force of gravity. Well, so imagine you have the Earth, and the Earth starts to make a particle that carries gravity. In the case of gravity, the particle is actually called the graviton. Okay? Now, the Earth creates a gravity particle called a graviton. But that gravity particle carries energy and mass. And so that gravity particle will itself feel the force of gravity, which means that it will also create more gravity particles. And each of those gravity particles will make more gravity particles. It will make more and more gravity, and so on and so forth. And this just keeps going and going and going. And everything just makes more and more gravity particles until in the end you have a disaster of gravitons. Okay? There's just a huge big mess. There are sort of too many gravitons. And this sounds like a bit of a strange and fluffy thing to say, but you can really show that this is happening at the mathematical level Just because you might someday encounter this thing in a class, I'll tell you what the word for this is. In the physics literature, the name for this, that there are too many gravity particles, is that the theory of quantum gravity is non-renormalizable. Okay? It's a very long word, but what it just means is there are too many gravity particles at short distances. Okay? And what that means is that basically we don't understand how to combine quantum mechanics and general relativity together. There's some sort of a problem here. Okay? And this is a problem with general relativity, that it doesn't play well with quantum mechanics, and this is something that many scientists are thinking about right now to try and understand. Okay. How do we solve this problem? Okay. How can we understand this? And there's one way in which you can solve this problem. Let me tell you what this is. This is, of course, this idea that is called string theory. Okay. So, well, what is string theory? Well, string theory is, again, a slightly radical sounding idea. So let me tell you what it means. You know how in our universe, it seems like there are many different kinds of particles, right? For example, there are electrons, there are these photons, there might be these gravity particles, there's things that are called gluons that I haven't told you about, but they're there. There's things called W and Z bosons. I realize I'm now just saying letters that you might not have heard of, but just trust me that there are many different kinds of particles in our universe. There are quarks. String theory has the following idea. String theory tells us that maybe, just maybe, instead of having all of these different kinds of particles, maybe we only have one sort of object which creates all of these. In other words, string theory says that instead of all these kinds of particles, maybe we just have one kind of string. Okay? In other words, all these things that look like particles are really just loops of string that vibrate in different ways. Okay? So imagine you have some small little loop of string. Now it's very, very small, this loop. So if you look at it from a big distance, it'll look like a particle. Okay? But this loop of string can vibrate in many different ways, and each way of vibrating will look like a different particle. For example, if it vibrates like this, it might look like the electron. If it vibrates in some other way, it might look like a photon. If it vibrates in some yet different way, it might look like a quark. And this is the idea behind string theory. Okay? So it's sort of nice because you see you get all these different kinds of particles from just one kind of string. So it's kind of economical, it's kind of elegant. But what's more interesting is that if you look at these patterns of vibrations, then this gravity particle that was so problematic before just comes out all by itself. Okay? The gravity particle is there. There is a certain vibrational pattern of this string that is exactly the graviton. Okay? And in fact, remember I told you about this problem that there are too many gravitons at short distances? This problem actually completely goes away, basically because this string has a certain size. And there's nothing really going on at scales that are smaller than the size of the loop of string. And that sort of deals with the issue of having too many particles. There's just basically nothing happening at sizes smaller than the string scale, and so that solves the problem completely. In other words, string theory is a perfectly nice theory of quantum gravity. Okay. Okay, so that's great. So, okay, we're done then. We can just stop and use string theory for everything. So I, of course, my research is on string theory, so I think it's extremely interesting. But it turns out it's not quite so simple as what I just said. So let me now tell you what people are working on right now to try and understand. Okay? So the first thing that is the issue with string theory is that actually you should ask, does it necessarily work? And the truth is, string theory only really works if you have 10 dimensions of space and time. In our universe, we don't have 10 dimensions of space and time. We have 3 dimensions of space and 1 dimension of time. In other words, we have 4. And so this is a problem because 10 is not equal to 4. So what that means is you have to take your extra 6 dimensions and find some way to curl them up into some tight little ball so you don't have to worry about them. Okay? But this is a confusing and complicated thing to do. And it turns out that there are many, many, many ways to do this. And each way of doing it actually gives you a slightly different universe with a slightly different pattern of particles. Okay? You get slightly different particles depending on how you curl up your extra dimensions. And it's difficult to see how to do this to get exactly our universe out. Okay? So that's one issue. Another issue is that in physics, we like to test our theories with experiments. So you might ask, can we do an experiment to test string theory? After all, I told you that we could do an experiment to test Einstein's theory of general relativity. We've done many such experiments and they've all worked. Can't we just do an experiment to test string theory? It turns out that we can't, at least not easily. Let me tell you why. You see, I told you there was an important length scale here, which is sort of the size of these little loops of string. You can ask how big are these strings, and you can try to estimate this. It turns out these strings are about 10 to the minus 35 meters long. Okay? This is an insanely small number. All right? When I say that insanely small, what do I really mean? I mean, there's a formula here, but it's so small that if you were to take an atom in your body and blow it up to fill the entire size of the observable universe, after doing that, one of the strings inside the atom would still only be 1 meter big. Okay? So this is an insanely small thing, and it is really hard to think of any experiment that can probe such small scales. And that is why string theory is difficult to test experimentally. However, we are still trying to make this connection, and you might hope there's some sort of an indirect experiment that we could do that would show that string theory does actually describe nature, although no one has been able to think of or perform such an experiment yet. So that's what all of you will have to do next. Okay, thank you everyone. It's been very nice being here. Take care.